Hi, Stu Schwartz, MasterMathMentor.com. This is video AB31. The topic is definite integrals with u-substitution. It covers the AB manual, pages 185 and 186. Hi, Stu Schwartz. Examine these curves. Y equals sine of x, square root of cosine x, on the intervals 0 to pi over 2. And y equals the square root of x on the interval 0 to 1. Two completely different shapes, two completely different sets of x intervals. One curve has a relative maximum, switching from increasing to decreasing, while the other curve is always increasing. And yet each has the same exact area. The integral from 0 to pi over 2 of sine x square root of cosine x dx is equal to the integral from 0 to 1 of the square root of x dx and is equal to 2/3. You can check it on your calculator. So how do we change the difficult looking integral on the left to the simple looking integral on the right? This video discusses definite integrals using u-substitution with a technique called changing the limits. Rather than explain the technique of changing the limits, we will look at a problem where we do not change the limits, and then the same problem when we do, and you can judge which way is easier. The problem is the integral from 0 to 2 of 2x times the quantity x squared plus 1 quantity cubed dx. We are not going to expand the expression. We're going to do the problem with u-substitution. So u is equal to x squared plus 1 and du is equal to 2x dx, which is already in the problem, so we don't have to do anything. So this problem becomes the integral of u to the third du, and that is u to the fourth over 4. But realize that u was a product of something that we created, so we have to change it back to x. So we started with x, we changed to u, but now we're going to go back to x. So this problem becomes the quantity x squared plus 1 raised to the fourth over 4 evaluated between 0 and 2. That is 5 to the fourth over 4 minus 1 to the 1 over 4, and that is 624 over 4, and the area is 156. Now let's do the same exact problem with changing the limits. It starts out the same. Our problem is the integral from 0 to 2 of 2x, quantity x squared plus 1, quantity cubed dx. Our u is x squared plus 1, and our du is equal to 2x. So this problem also becomes the integral of u to the third du. But now we will change the limits. When x is the lower limit, 0, u is 1. If x is the upper limit, 2, then u is 5. So this problem becomes the integral from 1 to 5 of u cubed du. Integrating, we get u to the fourth over 4 evaluated from 1 to 5. By changing the limits, everything is now in terms of u, so we do not have to change anything back to x. So this becomes 5 to the fourth over 4 minus 1/4, and we get the same answer, 624 over 4, which is 156. We show two curves. Y equals 2x, quantity x squared plus 1, quantity to the third, in blue, between 0 and 2, and the curve y equals x cubed, in red, from 1 to 5. Two different shapes, two different limits of integration, and yet their areas are exactly the same, 156. Hi, Stu Schwartz. Problem 2 reads the integral between 0 and 1 of x square root of 1 minus x squared dx. We will attack this without changing the limits. Our u equals 1 minus x squared. Our du is equal to negative 2x dx. We are missing the negative 2, so we'll put a negative 2 on the inside and a negative 1/2 to the outside. So this problem becomes negative 1/2 the integral of u to the 1/2 du, which is negative 1/3 u to the 3/2. We will now change everything back to x's, and we get negative 1/3 times the quantity 1 minus x squared raised to the 3/2 evaluated between 0 and 1. This gives negative 1/3 times the quantity 0 minus 1, and the answer is 1/3. We will now attack the problem by changing the limits. We start the same way. U equals 1 minus x squared and du is equal to negative 2x dx. We put a negative 2 to the inside and negative 1/2 to the outside. So this becomes negative 1/2 the integral of u to the 1/2 du. Let us now change the limits. If x is the lower limit, 0, then u is equal to 1. If x is the upper limit, 1, then u equals 0. So our integral is negative 1/2 the integral between 1 and 0 of u to the 1/2 du. We can make our life a little bit easier on ourselves by eliminating the negative 1/2, make it positive, and changing the order of the limits. So this becomes 1/2 the integral from 0 to 1 of u to the 1/2 du. Doing this eliminates a lot of negative signs. So we get 1/2 times 2/3 u to the 3/2 evaluated between 0 and 1, and we get 1/3 times the quantity 1 minus 0, which is equal to 1/3. As mentioned, the advantage in this technique is eliminating negative signs that can make things a little bit tricky. Hi, number 3 reads the integral from 0 to pi over 4 of sine of 2x dx. Doing the problem without changing the limits, u is equal to sine of x and du is equal to 2 cosine of 2x dx. A 2 goes to the inside, a 1/2 goes to the outside. So this becomes 1/2 the integral of sine u du, which is negative cosine u over 2. So changing back to x, we get negative cosine of 2x over 2 evaluated between 0 and pi over 4. So this becomes negative cosine of pi over 2, which is negative plus 1/2 cosine of 0. And our answer turns out to be 1/2. Attacking the same problem by changing the limits, we start the same way. U equals 2x and du is equal to 2 dx. And our integral becomes 1/2 the integral between 0 and pi over 4 of 2 sine 2x dx. But let's change the limits. If x equals 0, u is equal to 0. If x is equal to pi over 4, u equals pi over 2. So this problem becomes 1/2 the integral between 0 and pi over 2 of sine of u du. And that is negative cosine of u over 2 evaluated between 0 and pi over 2. We get the same answer, negative 1/2 cosine of pi over 2 plus 1/2 cosine of 0. Answer is 1/2. While you are never forced to do a problem by changing the limits, a typical multiple choice AP question could ask you which of the following is the original integral equal to or equivalent to, and you would then have to understand the technique of changing the limits. Hi, Stu Schwartz. Numbers 4 and 5 ask to find the definite integral of an expression. You can choose to change the limits or not, and verify your answers on the calculator, either by graphing it or just asking for the definite integral between the given limits. Number 4 asks for the integral from 0 to the square root of 5 of x over the square root of x squared plus 4 dx. To start this, we let u equal x squared plus 4 and du is equal to 2x dx. We multiply by 2 on the inside of the integral and 1/2 on the outside of the integral. And this becomes 1/2 the integral of u to the negative 1/2 du. We now change the limits. When x is equal to 0, u is equal to 4. You might have thought it strange that one of your limits of integration was the square root of 5, but there is a reason for it. When x is the square root of 5, we get a nice value of u, which is 9. So this becomes 1/2 the integral of 4 from 4 to 9 of u to the negative 1/2 du, which is u to the 1/2 evaluated between 4 and 9. And that becomes 3 minus 2, which is exactly 1. Number 5 was our example problem, the integral from 0 to pi over 2 of sine x square root of cosine x dx. We let u equal cosine x and du is equal to negative sine of x dx. So we need a negative on the inside and a negative on the outside, becoming negative the integral from 0 to pi over 2 of negative sine x square root of cosine x dx. Changing to u's, we get negative integral of u to the 1/2 du. We change the limits. When x is equal to 0, u is equal to 1. When x is equal to pi over 2, u is equal to 0. So we have negative the integral from 1 to 0 of u to the 1/2 du. We can get rid of the negative sign by reversing the limits, and this becomes the integral from 0 to 1 of u to the 1/2 du, which is 2/3 u to the 3/2 evaluated from 0 to 1, and our final answer is 2/3. Hi, Stu Schwartz. 6 and 7 are 2 more problems to find the definite integral, and they are slightly more complicated than the previous 2. 6 reads the integral from 0 to pi over 6 of 1 plus sine x cosine x dx. When we do this problem, we realize that we need to split it into 2 integrals. So this becomes the integral from 0 to pi over 6 of 1 dx plus the integral from 0 to pi over 6 of sine x cosine x dx. The first part of the problem is fine. There's no need to do any changing of limits. But the second one, we need to use u-substitution. So our first integral is from 0 to pi over 6 of 1 dx. But for the second integral, u is sine x, du is cosine x dx. And we change the limits. When x is equal to 0, u equals 0. When x equals pi over 6, u is equal to 1/2. So the second integral becomes the integral from 0 to 1/2 of u du. So our final result will be x evaluated from 0 to pi over 6 plus u squared over 2 evaluated from 0 to 1/2. And we end up getting pi over 6 plus 1/8. This type of problem occurs frequently, and students sometimes attempt to change the limits for both pieces, while the only one of the integrals needs to be done in terms of u-substitution. Number 7 reads the integral from 0 to the square root of pi over 2 of x sine of pi minus x squared dx. We let u equal pi minus x squared and du is equal to negative 2x dx. So we multiply by negative 2 on the inside and negative 1/2 on the outside, getting negative 1/2 the integral from 0 to the square root of pi over 2 of negative 2x sine of pi minus x squared dx. Changing into u, we get negative 1/2 the integral of sine u du. We change the limits, and when x is equal to 0, u is equal to pi, and when x is equal to the square root of pi over 2, u turns out to be pi over 2. So we have negative 1/2 the integral from pi to pi over 2 of sine u du. We can kill two birds with one stone by changing the negative into a positive and reversing the order of integration, allowing us to have the smaller limit on the bottom. So we have 1/2, and the integral of sine u is cosine of u evaluated from pi to pi over 2. We get 1/2 times the quantity 0 plus 1, and our answer is 1/2. Hi, Stu Schwartz. On the AP exam, it is difficult for testers to test student ability of taking definite integrals if they are allowed to use their calculators. Why go through the messy routine of u-Substitution when they could just plug the problem right directly into the calculator and get an answer? These problems were specially constructed so that a calculator is of no help in calculating definite integrals. We are told that the integral from 0 to 1 of f of x dx equals 6, the integral from 0 to 2 of f of x dx equals 4, and the integral from 0 to 4 of f of x dx is equal to negative 8. We are first asked for the integral from 0 to 2 of f of 2x dx. We do this with u-Substitution. We let u equal 2x and du equals 2 dx. So we need a 2 on the inside, a 1/2 on the outside, and this problem becomes 1/2 the integral from 0 to 2 of 2 f of 2x dx. Changing into u, we have 1/2 the integral of f of u du, and now we change the limits. If x is equal to 0, u is equal to 0. If x is equal to 2, u is equal to 4. So we have 1/2 the integral from 0 to 4 of f of u du. The integral of f of u du is negative 8 from 0 to 4, so 1/2 of negative 8 is negative 4. In number 9, we're asked the integral from 0 to 2 of f of 1/2 x dx. We let u equal 1/2 x and du is equal to 1/2 dx. So we put a 1/2 on the inside and a 2 on the outside. And this becomes 2 integral of f of u du. Changing the limits, if x equals 0, u equals 0. If x equals 2, u is equal to 1. So we have 2, the integral from 0 to 1 of f of u du. That integral is 6, and therefore 2 times 6 is equal to 12. Finally, we have the integral from 1 to 2 of f of 2x dx. u equals 2x, du equals 2 dx, 2 on the inside, 1/2 on the outside. So we have 1/2 the integral 1 to 2 of 2 f of 2x dx. And that becomes 1/2 the integral of f of u du. Changing the limits, when x is equal to 1, u is equal to 2, and when x is equal to 2, u is equal to 4. So we have 1/2 the integral from 2 to 4 of f of u du. We are not given that integral. However, we do know that the integral from 2 to 4 is the integral from 0 to 4 minus the integral from 0 to 2. So we have 1/2 the integral of the quantity, the integral from 0 to 4 of f of u du, minus the integral from 0 to 2 of f of u du. And we have then 1/2 times the quantity, negative 8 minus 4, answer negative 6. Hi, Stu Schwartz. The integral of 1 over x dx cannot be performed by the power rule. We would get x to the 0 over 0, which does not exist. So in our next video, we're going to expand our ability of taking integrals. That's what's coming up in the next video.